goal of the UC6 prototype is to provide evidence of the broader applicability of the tools and techniques developed in the Tuparma project. We wanted to demonstrate the integration of the runtime resource manager, runtime monitoring, dynamic memory management, design space exploration, and knock trace technology within the context of the project.
The prototype mimics a surveillance system where a set of reconfigurable applications are capable of changing some parameters in order to adapt themselves to runtime application requirements and available platform resources. The application requirement corresponds to any possible threat which is detected in the scene. We assume that the restricted area is observed with a pair of parallel stereo cameras, and that the raw video is compressed at the source before being sent through the network to our prototype. We used the scalable video coding to compress the input video, since this standard allows to select the layer to be decoded, and each layer corresponds to different quality and different frame rate. We applied the Tuparma methodologies to design an adaptive system with the following reconfiguration policy. Whenever a person is approaching the cameras, which corresponds to someone entering a restricted area, the system automatically increases the frame rate and the quality of the decoded frames. On the one hand, this requirement allows the surveillance team, who represents the application user, to better see the details of the scene, for example, to recognize the face of the people approaching the cameras. On the other hand, the higher frame rate is necessary for the system to promptly react to external events, such as fast movements, and meet soft real-time constraints. There are three possible configurations that are internally mapped to some distance thresholds. A short distance configuration, where the SVC decoders decode the highest layer, which corresponds to highest frame rate and highest quality, and at the same time, Multiview is running in its highest operating point to ensure high throughput and fast response time. Then there is a mid-distance configuration where the application requirements are relaxed in order to reduce the application workload on the platform. And finally, a configuration which corresponds to long distance, or the case where no movement is detected in the scene. And in this configuration, Multiview is disabled, while the SVC decoders only decode the lowest layer.
The prototype integrates 5 different technologies developed within the Tuparma project. Specifically, it integrates the Multiview application, which is a stereo matching application for computing the distance of the moving objects within the scene, and 2 SVC decoders for decoding the input video stream and also reconfiguring the temporal and the quality layers of the scene according to the identified scenario. More specifically, the first introduced technology is a new OpenCL implementation of Multiview application, a MIME implementation of SVC decoders that they are adaptable according to the identified scenarios. Also, during runtime, we introduce the barbecue runtime management system to orchestrate the resource allocation shared and used among the different instantiations of the application. And also the dynamic memory management system that provide the memory allocation mechanism for different scenarios of the running applications. We have to specifically note that the multi-view application, the OpenCL version of multi-view application, exposes a large number of parameters, both at the application level and also regarding the OpenCL runtime layer. That is a very difficult task to be optimized alone from the designer. So, in this specific point, we introduce also the most design space exploration tool in order to automatically explore and analyze the trade-offs of different decisions according to the application and runtime specific parameters exposed by the application. Using the automated exploration, we further extended the runtime system to be application specific and use the extracted optimized operation points during runtime in order to provide sustainable performance for OpenCL implementation. A last note is that the complexity of the provided prototype can be also seen from the fact that it enables the cooperation and management of two different runtime systems, the OpenCL runtime system required from multi application and the mine runtime system required from the SVC decoders.
First, we start the Barbecue Runtime Resource Manager, which initializes the multi-core platform into a host node for system processes and one or more device nodes where the applications will be deployed. This is the output of the prototype. In the left window, the decoded video captured by one of the stereo cameras shows the surveyed area. In the right window, we show the runtime configuration of the SVC decoders and multiview. At the beginning, nothing is happening in the scene, so the configuration ID of the SVC decoders is 0, which corresponds to the lowest SVC layer. This is why the quality of the output frame is poor. In the multiview configuration, you can see that the power saving mode is on, which means that multiview is disabled. Then we start the prototype, which will remain in the power saving configuration until any possible threat is detected in the scene. This is the case when a person enters the surveilled area, which triggers a reconfiguration of the system. Now the system is running in a mid-distance configuration since the detected object is moving away from the cameras. In this configuration, multiview ensures a response time less than 1 second, while providing a good quality of service, which means an accurate estimate of the distance. The long-distance configuration, when the object is far away from the cameras, brings the system back to the power-saving mode. Another person enters the area, so the system is reactivated. The previous person is approaching the cameras. When he gets over a distance threshold, then the highest configuration will be triggered. Now, you can see that the SVC decoders are decoding the highest layer, which corresponds to 15 frames per second, while before the frame rate was 7.5, and at the same time the quality of the output video is much better now. The time constraint on multiview is higher, so the application-specific monitor reduces the accuracy of the distance estimate to meet the frame rate goal, 2.5 frames per second. The goal is met since the measured frame rate is above the goal, which provides a response time less than 500 milliseconds. In this plot, we compare our prototype above with the baseline version that does not use the Barbecue Runtime Resource Manager below. The multiview runtime requirement, frame rate, depends on what is detected in the scene, so it should be the same since the input video used for the two implementations is the same. A first result is that our proposed prototype is more stable at runtime in following the frame rate goal. Besides that, the baseline version misses a possible threat in the scene, which is when the second person gets close to the cameras. Indeed, the frame rate goal is not increased to 2.5 frames per second as in our proposed prototype. This does not guarantee a good response time in the baseline version.